Hi there, welcome back to the Logic of Risk. This is episode 11, and we are nearing the end of our overview of probability definitions. In a couple of weeks, we will return to risk and how to quantify it. So, what are we dealing with today? Today, we are talking about logicism, while in the next episode, we will complete our journey with the axiomatic definition of probability. Let's go! So far, we have discussed objectivism and subjectivism, diving into the debate between those who view probability as something objective, existing in itself, and those who argue that probability cannot be separated from the subject, since it is formed in our minds and expresses our beliefs, inclinations, knowledge, context, and even our fears when facing what is random. Apart from this dispute, there is the classical definition, which does not belong to the discussion due to historical reasons and its extreme limitations. As I have mentioned several times, there are other definitions. Some try to bridge the gap between objectivism and subjectivism, and that's the case with logicism. Others resolve the issue in a metaphysical way, abstracting themselves, choosing not to decide or get their hands dirty, and instead focusing on the mathematical properties and uses of probability. That's the case with the axiomatic definition. There are a few other minor schools, but we won't consider them. This choice is mainly due to two reasons. Reason number one: some are merely refinements of what we have already discussed, which would lead us too deep into the details. A typical example is the predictive definition, which in its classical version is highly limiting and often flawed, suffering tremendously from historical bias and other issues, and in its modern version is nothing more than a nuance of the empirical Bayesian approach. Reason number two: some definitions are purely speculative, with applications of little or no interest for us, not to mention that they are often not even clear in their implications. One example is the best systems definition introduced by David Lewis, now a somewhat trendy topic in certain circles. From one point of view, it's a kind of propensity-based approach, but it tries to improve the treatment of individual phenomena by borrowing from the epistemic perspective. To be honest, some of my colleagues might even spare you the logicist discussion for this very reason, but personally I would consider that a grave mistake. If it is true that for a long time the logicist view of probability was confined to academic debates, the recent resurgence of machine learning techniques is now leading to a practical application of the logicist definition. Notice that I use the word resurgence because the first neural networks date back to the 1940s. Only back then we didn't have enough computing power. Some might then say that, in the end, logicism is nothing more than the Bayesian approach in disguise, but let's take it step by step. Do you remember when a few episodes ago I mentioned Jaynes and his idea of probability as the logic of science, which is also the title of his monograph? Well, the logicist definition of probability does just that. It attempts to go beyond classical logic, where a given proposition, which for us becomes an event, can only assume two values: false and true, or 0 and 1 if we use Boole's coding. For example, the proposition the speaker of this podcast is named Pasquale is true and takes the value 1. while the speaker of this podcast is named John, is false and takes the value 0. Now, strictly speaking, I know one of these propositions is true and the other false. But someone might think I have two names. I have not excluded this possibility. So my being called Pasquale John would be an option to consider. Therefore, we might refine our propositions by saying the speaker of this podcast has only one name, and it is Pasquale, similarly for the version with John. Now, classical propositional logic and its various evolutions work very well and allow us to describe and solve a host of fundamental problems. Just think how essential that Boolean 0-1 coding is in computer science. However, and this is a big however, there are many situations where the truth or falsity of a proposition isn't so black or white. We might face partial truth or falsehoods either because our knowledge is limited, because we are talking about the future, or because a dichotomous description would be forced. If I say that tomorrow will be sunny, today I have no way to assert whether that statement is completely true or completely false. And if I mention rain, there is a significant difference between a few drops and a torrential downpour. Consider an object you are holding in your hands, whose temperature you must describe. In a Boolean dichotomous world of zeros and ones, that object would be either cold or hot. But we all know that an object can also be lukewarm. And what does cold mean exactly? Is it cold enough that you can still hold it, or so cold that touching it would instantly freeze your fingers and send you running? The same applies to hot. Is it a manageable warmth or is it scorching? A lukewarm object is one that is neither hot nor cold. It might be 50% cold and 50% hot, or perhaps 40% cold and 60% hot, and so on. In such cases, using only two truth values, false and true, cold or hot, would be very limiting. Sure, in some situations, I could string together concatenations of zeros and ones, like, is it cold? If yes, how much? And if a lot, then really a lot. But that would be cumbersome and dreadfully boring, even if that's how our computers, so to speak, simplify things. So, in the evolution of mathematical logic, there have been various attempts to handle these non-strictly dichotomous situations. A famous example is fuzzy logic. But what does all these have to do with probability? I know you are eager. Now imagine that 0 and 1 don't mean false and true, but rather that a given event is impossible, 0, or certain, 1. Or, even better, that it either does not happen or does happen. Every value between 0 and 1 then becomes a quantifier of the possibility of our event happening. A certain event takes the value 1, an impossible event takes the value 0. A moderately possible event might have a value of, say, 0.5, while values like 0.2 or zero point 0.8 would represent events that are scarcely or very likely, and so on. In the logicist view of probability, probability expresses the degree of possibility of a proposition of an event. It indicates how true that proposition is, hence how certain, or false, hence how impossible. More precisely, it expresses the extent to which one proposition informs us about the certainty and truth of another. That's why probability can be seen as the new logic of science. It allows us to handle nuances, to describe the many situations in which we can't say that something is simply true or false, and in which we must reason in terms of possibility. Logically, probability allows us to manage contingency. This management of contingency is one of the key points embraced by analytical philosophy. The logicist view of probability is widespread among analysts, who have been studying and dissecting it for decades, with results of absolute significance. Among them, one cannot fail to mention the great Kripke, a giant of analytical philosophy, a prodigy, and one of the foremost exponents of modal logic, intuitionist logic, and many other areas. Though generally little known to the public, Kripke is one of the minds who has most influenced modern scientific debate. But as fascinating and powerful as these logical discussions are, let's set aside contemporary analytical philosophy for now and take a leap back in time to the founding fathers of the logicist view. Some names we have already mentioned include Wittgenstein, Weismann, Keynes, Reichenbach, Keyborg, Nielsen, Russell, Carnap, Jaynes, and, in some respects, even Jeffreys, whom we encountered among the subjectivists. I could list many more, but I would like to avoid a shopping list. In fact, the logicist view of probability goes much further back in time. In a way, both frequentist and subjectivist intuitions can be found in writings from the 1500s and the 1600s, if not even in ancient Greek and Latin texts. In the case of logicism, one might even call upon scholasticism, Catholic probabilism, probabiliorism, lessism, and the many learned theological debates. But once again, let's try to keep things within about 20 minutes, so we will jump directly to the 20th century. In his Tractatus Logico-Philosophicus, Wittgenstein hints at his own view of probability, a view later independently expressed by John Maynard Keynes in his treatise on probability, a work highly praised by Russell. You can, of course, buy the Tractatus, but you can also find it on wittgensteinproject.org in various languages. In proposition 5.153, Wittgenstein writes, quote, "A proposition is in itself neither probable nor improbable. An event occurs or does not occur. There is no middle course." Unquote. Then, in proposition 5.155, he adds, quote, "The minimal unit for a probability proposition is this: the circumstances of which I have no further knowledge give such and such a degree of probability to the occurrence of a particular event." Unquote. And in proposition 5.156, he concludes, quote, "It is in this way that probability is a generalization. It involves a general description of a propositional form. We use probability only in default of certainty, if our knowledge of a fact is not indeed complete, but we do know something about its form." Unquote. It reminds me a bit of Laplace demon. I don't know about you. In Wittgenstein's view, probability is a way to assign a degree of truth to propositions to which I cannot assign an absolute true or false value. If I don't have full certainty about what will happen tomorrow in a given situation, I can use probability to manage that indeterminacy. The natural question that arises at this point, given everything we have discussed so far, is: okay, Wittgenstein, we accept this idea of probability as an extension of logic, but Is that number between 0 and 1 objective or subjective? I will answer with a question. Do you remember when I said that, in my view, logicism bridges objectivists and subjectivists? Well, among the various logicists, some lean toward the objectivist perspective, while others favor the subjectivist one. In Wittgenstein's case, if we look at the evolution of his thought, it is not easy to reach a clear answer, even though we could talk about it for hours. Among the objectivist logicists, we find Keynes, as I mentioned in the previous episode. Let's read together what Keynes writes in his treatise. Quote, in the sense important to logic, probability is not subjective. It is not, that is to say, subject to human caprice. A proposition is not probable because we think it so. When once the facts are given which determine our knowledge, what is probable or improbable in these circumstances has been fixed objectively and is independent of our opinion. The theory of probability is logical, therefore, because it is concerned with the degree of belief which is rational to entertain in given conditions, and not merely with the actual beliefs of particular individuals, which may or may not be rational. Unquote. So, for Keynes, probability is the study of the reasons that lead us to have a certain rational preference for one belief over another. Is this really objective? Well, we will see. Alright, let's stop here. We will pick up from here next week. I know you can't wait. Ciao ciao!